Hey, my name is Tim Lickerswitter. I'm a cybersecurity researcher at Osnabrück University. In this video, I will present you a new malware class called Phantom Malware. This malware class conceals all of its malicious actions as impersonated user activity. Metaphorically speaking, a phantom malware is acting as an additional user and masks its actions from the real current user. Both users are acting concurrently, with the difference that the current user, human, does not notice the activity of the hidden user phantom malware. I will present you the basics of phantom malware and the proof of concept. Thereafter, I will introduce you the concept of Phantom Ransomware. For the operating system and antivirus software, it mistakenly looks like that the user itself is overriding, in this case encrypting, its own files. In order to prevent that the real user became suspicious while seeing the imitated user actions, Phantom Malware hides these by applying an additional desktop. First of all, the window explorer is opened on the additional desktop. Thereafter, the malicious command is inserted in the input box of the window explorer and confirmed for execution. As a consequence, the window explorer process launches a CMD process which executes the command. The command contains a redirection operator, therefore the command output is written into a file. The Phantom Malware reads this file. The file content representing the command output is analyzed if the command was executed successfully. Hence, Phantom Malware can react in error cases. Overall, the file acts as a hidden information channel for the Phantom Malware containing outputs of its executed commands. Just note, in this video I applied the window explorer. Another window can be used containing an input box which is able to execute the inserted command. For example, the CMD or the run dialog box. Here's an example for the additional desktop usage by the Phantom Malware. On the current desktop, the victim is watching a cute cat video on YouTube. Meanwhile, on the additional desktop, the Phantom Malware inserts a malicious command in the input box of the window explorer and confirms it for execution. However, the victim does not notice these actions because these do not happen on its current desktop. In other words, these actions happen out of sight of the victim. In the following, I will present you a C++ implementation for Windows 10 as a proof of concept for the impersonated user actions on the additional desktop. First of all, the additional desktop is created by applying the WinAPI function createDesktop and checked if this creation was successfully. Instead of creating an additional desktop, an already existing desktop may be used. The already existing desktop, however, must not be in focus at the time. Note, the desktop is giving a name for identifying it later. Accordingly, the running thread is assigned to this desktop by applying setThreadDesktop. This thread assignment enables the window monitor to receive information about opening windows on the additional desktop. Furthermore, there's a check if this assignment was successfully. The window monitor is just a helper object which returns a list of window handles which are opened during the measure interval. In the following, it is used for identifying the window handle of the window explorer. Next, the window monitor starts to listen. To open the window explorer on the additional desktop, create process is called. The value LP desktop of the startupInfo struct is a pointer to the additional desktop's name. This name was defined in the first step. The startupInfo struct is passed as a parameter when calling createProcess. Besides, a process information struct is passed as a parameter for receiving a process handle. This handle is checked if the process creation was successfully. After a waiting time of approximately 3000 milliseconds, the window monitor stops listening. The waiting time secures that system processes perceived the opening of the window explorer. Now, we use the window monitor to get a pointer to a buffer, and in this buffer there are window handles for each window which are opened during the measure interval. Besides, we pass a variable during this function call, and in this variable is the amount of windows written in it which are opened during the measure interval. And we know we opened only one window, and hence the first element in this buffer is the window handle of the window explorer. Afterwards, post message is applied to send a VM key down message with F4 to the Window Explorer in order to bring its input box in focus. By the way, a VM key down message represents a key event. After the Window Explorer receives a VM key down message with a 4, it starts a scrolling animation before its input box gets editable. The waiting time of 1000 milliseconds secures that system processes responsible for the GUI perceive the focus change and this animation is over. So, just for demonstration purpose, this is the Window Explorer. Now I press F4. We have here the scrolling animation and there is a default text written in it. And the next goal is to remove this default text. The window handle of the input box will be determined by identifying the focused window element of the Window Explorer. For this identification, the Window API call getGUI-thread-info is applied. A GUI-thread-info struct is passed as a parameter. Besides, we must identify the thread ID of the Window Explorer, which is also passed as a parameter. After the function call of getGUI-thread-info, the HVND focus value of the GUI-thread-info struct represents the window handle of the input box of the Window Explorer. And now we can remove this default text by sending VM key down messages with backspace to this input box. Just note, there's a waiting time of 25 milliseconds because the operating system needs time to process these messages. And we are able to send messages to the input box on the additional desktop because we assign in the second step here the running thread to the additional desktop. By default, this thread is assigned to this desktop here on which it was created. Now the input box is clean, there's no text in it. Now we start to insert the command in this input box. We do this by sending for each of its characters a corresponding VM char message. So in other words, command is inserted character by character. Here again, there's a waiting time between these messages. The command inserted in the input box of the Window Explorer has the following form: cmd.exe/c, and then the real command. In this case, it's just an echo redirected in the file. And finally, we can confirm the command for execution by sending a VM key down message with enter. Now we wait a second because the operating system needs time to execute the command on the additional desktop. And finally, we do some cleanup by terminating the Window Explorer process and closing the additional desktop. And now I will compile and execute this proof of concept. And the command is executed. Here's the file, it's the file content. As you can see, we got an RTL code execution as trusted system user. The previous presented technique for the mimicked user actions is called user imitating. Based on this, a file encryption for Phantom Ransomware can be developed. It is assumed that the file foo.jpg shall be encrypted. First of all, this file is copied to another folder. In this example, this folder is c/bar. By copying this file, it is renamed to abc. For this action, user imitating is applied. The output of the corresponding command is redirected into the file output.txt and analyzed if an error occurred, such as not having access rights. Next, the Phantom Ransomware reads the file abc without employing user imitating. In other words, the Window API call read file is applied. Now, the corresponding encrypted file content will be determined. Thereafter, user imitating is applied to overwrite foo.jpg with the encrypted content. To overwrite this file, two commands in combination with the redirection operator are used. Each command output is redirected to output.txt and read by the Phantom Ransomware. This is done to detect any errors that may have occurred during file overriding, for instance, no file writing privileges. Every file to encrypt is renamed to ABC while being copied. Because the file ABC already exists, its previous file content will be overwritten completely with the content of the copied file. In this example, foo.jpg, user imitating is applied for concealing this copy command and the file overriding as user activity. As a consequence, for the operating system and the antivirus software, it looks like that the same file in this example, ABC, is read in a sequence by the Phantom Ransomware and the victim overrides, in this case, encrypts their own files. So that's all. Thank you for your attention. Feel free to ask questions in the comment section below. If you want more information about this topic, you can read my paper on the IEEE Explorer. The link is in the description of this video. Bye.